Engines are the beating hearts of countless machines that power our world. From cars and motorcycles to lawnmowers and chainsaws, these incredible devices transform fuel into mechanical energy, enabling motion and work. Understanding the different types of engines and their operating principles is key to appreciating the ingenuity behind their design and function. This essay delves into the fascinating world of internal combustion engines, exploring their classification, operation, and performance characteristics. Engines are broadly classified based on two key factors: the type of fuel they utilize and their operating cycle. Internal combustion engines, the focus of this essay, burn fuel within a closed chamber to generate power. These engines can be further categorized as either spark ignition, SI, or compression ignition, CI engines, depending on how the fuel-air mixture is ignited. In SI engines, commonly found in gasoline-powered vehicles, a spark plug ignites a pre-mixed fuel-air charge. In contrast, CI engines, often used in diesel-powered vehicles and machinery, rely on the heat generated by compressing the air to ignite the fuel injected into the combustion chamber. This fundamental difference in ignition methods leads to variations in engine design, performance characteristics, and emissions. Understanding the distinctions between SI and CI engines, as well as their respective operating cycles, is crucial for comprehending the diverse applications and capabilities of these remarkable machines. By delving into the intricacies of engine design and function, we can gain a deeper appreciation for the engineering marvels that propel our modern world. Internal combustion engines, the workhorses of modern transportation and industry, derive their power from the controlled combustion of fuel within a confined space. Unlike external combustion engines, such as steam engines, where combustion occurs outside the engine, internal combustion engines directly harness the expansive force of burning fuel to drive mechanical motion. At the heart of every internal combustion engine lies a cylinder, typically a cylindrical chamber, housing a piston that moves back and forth. This reciprocating motion of the piston is converted into rotary motion, which ultimately powers the wheels of a vehicle or drives other machinery. The combustion process within the cylinder is a carefully orchestrated dance of fuel, air, and ignition, designed to extract maximum energy from the fuel while minimizing waste and emissions. The fuel, whether gasoline, diesel, or other combustible substances, is mixed with air in precise proportions to create a combustible mixture. This mixture is then introduced into the cylinder, where it is compressed by the piston. The compressed mixture is ignited either by a spark from a spark plug in SI engines or by the heat of compression in CI engines, causing a rapid expansion of gases. This expansion of gases exerts a powerful force on the piston, pushing it downwards and initiating the engine's power stroke. The reciprocating motion of the piston is transmitted to a crankshaft via a connecting rod, converting the linear motion into the rotary motion that drives the vehicle or machinery. Understanding the principles of internal combustion is essential for appreciating the ingenious design and operation of these ubiquitous powerhouses. Two-stroke engines, known for their simple design and high power-to-weight ratio, complete a power cycle with just 2 strokes of the piston or 1 revolution of the crankshaft. Unlike their 4-stroke counterparts, two-stroke engines lack dedicated valves for intake and exhaust, relying instead on ports in the cylinder wall that are covered and uncovered by the piston's movement. This simplified design, while offering advantages in terms of compactness and weight savings, comes with certain trade-offs. The absence of dedicated valves necessitates the mixing of lubricating oil with the fuel, as the piston cannot effectively lubricate the cylinder walls on its own. This oil-fuel mixture is then drawn into the crankcase, which acts as a temporary reservoir before being transferred to the combustion chamber. As the piston moves upwards, it compresses the fuel-air mixture in the combustion chamber, while simultaneously drawing a fresh charge of fuel-air mixture into the crankcase through the intake port. When the piston reaches the top of its stroke, ignition occurs, either by a spark or compression, forcing the piston downwards. During this downward stroke, the piston first uncovers the exhaust port, allowing the burnt gases to escape. Further downward movement uncovers the transfer port, allowing the fresh fuel-air mixture from the crankcase to flow into the combustion chamber. The upward stroke then repeats the cycle, compressing the fresh charge and expelling the remaining exhaust gases. This continuous cycle of intake, compression, combustion and exhaust occurring within 2 strokes of the piston makes the 2-stroke engine a compact and powerful, albeit less efficient and more polluting, alternative to its 4-stroke counterpart. 4-stroke engines, the dominant type of internal combustion engine in automobiles and many other applications, operate on a more complex but ultimately more efficient cycle than their 2-stroke counterparts. As their name suggests, 4-stroke engines require 4 strokes of the piston or 2 complete revolutions of the crankshaft to complete one power cycle. This cycle consists of 4 distinct stages: intake, compression, power and exhaust. During the intake stroke, the piston moves downwards, drawing in a fresh charge of fuel and air through an intake valve located in the cylinder head. As the piston reverses direction and moves upwards, the intake valve closes and the trapped fuel-air mixture is compressed. This compression stroke significantly increases the temperature and pressure of the mixture, preparing it for ignition. At the top of the compression stroke, ignition occurs, either by a spark from a spark plug in gasoline engines or by the heat of compression in diesel engines. The resulting combustion rapidly expands the gases, forcing the piston downwards in a powerful stroke that constitutes the engine's power phase. As the piston nears the bottom of its stroke, the exhaust valve opens, allowing the burnt gases to be expelled from the cylinder by the upward-moving piston during the exhaust stroke. This completes one full cycle of the 4-stroke engine, with the process repeating continuously to generate power. The 4-stroke cycle's separation of intake, compression, power and exhaust strokes allows for a more controlled and efficient combustion process, making it the preferred choice for a wide range of applications. Section 5. Mapping the engine's heartbeat. Indicator diagrams. Indicator diagrams, graphical representations of the pressure changes within an engine's cylinder during one complete cycle, provide valuable insights into the engine's performance characteristics. These diagrams, traditionally obtained using mechanical indicators but now commonly generated electronically, plot cylinder pressure against piston displacement or crank angle. The shape of the indicator diagram reveals crucial information about the combustion process, valve timing, and overall engine health. The area enclosed by the diagram represents the work done by the gases on the piston during one cycle. Analyzing this area allows engineers to calculate the engine's indicated power, a measure of the power developed within the cylinder. Theoretical indicator diagrams based on idealized thermodynamic cycles serve as benchmarks for comparison with actual engine performance. Actual indicator diagrams, obtained from real-world engine testing, deviate from the ideal due to factors such as heat transfer, friction losses, and the complexities of the combustion process. Comparing theoretical and actual indicator diagrams helps engineers identify areas for improvement in engine design and operating parameters. By analyzing the shape and characteristics of these diagrams, engineers can optimize valve timing, combustion chamber design, and other factors to enhance engine efficiency, power output, and emissions performance. Indicator diagrams, therefore, serve as invaluable tools for understanding and improving the performance of internal combustion engines. Section 6. Power and efficiency measuring engine performance. Evaluating engine performance involves assessing its power output and efficiency, both crucial factors in determining its suitability for various applications. Indicated power, calculated from the area enclosed by the indicator diagram, represents the theoretical power developed within the cylinder, while brake power measures the actual power delivered to the output shaft. The difference between indicated power and brake power reflects the frictional and mechanical losses within the engine, such as friction between moving parts and energy consumed by auxiliary components like the oil pump and alternator. Mechanical efficiency, defined as the ratio of brake power to indicated power, quantifies these losses. Thermal efficiency, another crucial performance metric, measures how effectively the engine converts the chemical energy stored in the fuel into useful work. It is defined as the ratio of the work output to the heat input from the fuel. Higher thermal efficiency indicates that a greater proportion of the fuel's energy is being utilized, leading to better fuel economy and reduced emissions. Factors influencing thermal efficiency include compression ratio, combustion chamber design, and operating conditions. Engineers strive to maximize both mechanical and thermal efficiency to improve engine performance, reduce fuel consumption, and minimize environmental impact. Understanding and optimizing these efficiency parameters are paramount in developing cleaner, more sustainable, and high-performing engines. Section 7. Timing is everything. Valve and port timing diagrams. Valve and port timing diagrams are graphical representations of the precise timing of valve and port openings and closings relative to the position of the crankshaft. These diagrams are crucial for understanding and optimizing the flow of gases into and out of the cylinder, which directly impacts engine performance. In four-stroke engines, valve timing diagrams illustrate the opening and closing points of the intake and exhaust valves in degrees of crankshaft rotation. The timing of these events is carefully orchestrated to maximize the amount of fresh charge entering the cylinder during the intake stroke and to effectively expel the burnt gases during the exhaust stroke. Two-stroke engines, lacking dedicated valves, rely on ports in the cylinder wall that are covered and uncovered by the piston's movement. Port timing diagrams for two-stroke engines depict the opening and closing of the intake, transfer, and exhaust ports relative to the piston's position. The timing of these events is critical for controlling the flow of fuel-air mixture into the cylinder and for scavenging exhaust gases. Optimizing valve and port timing is essential for achieving desired engine characteristics. Early or late valve or port openings and closings can significantly affect engine performance, influencing factors such as volumetric efficiency, torque output, and emissions. Precise timing ensures efficient gas exchange, maximizing power output and minimizing fuel consumption. Section 8. Igniting the charge combustion in SI and CI engines. Combustion, the heart of the power generation process in internal combustion engines, involves the rapid chemical reaction between the fuel-air mixture and oxygen, releasing heat and producing exhaust gases. Spark ignition or SI and compression ignition or CI engines, however, employ distinct methods to initiate and control this combustion process. In SI engines, commonly found in gasoline-powered vehicles, a spark plug ignites a pre-mixed fuel-air charge drawn into the cylinder during the intake stroke. The spark, timed to occur near the end of the compression stroke, creates a flame front that propagates through the compressed mixture, causing a rapid increase in pressure and temperature. This expansion of gases forces the piston downwards, generating power. CI engines, widely used in diesel-powered vehicles and machinery, operate on a different principle. Instead of a spark plug, CI engines rely on the heat generated by compressing the air to a much higher degree than in SI engines. Fuel is injected into this hot compressed air towards the end of the compression stroke, and it ignites spontaneously due to the high temperature. Combustion in CI engines is therefore controlled by the timing and rate of fuel injection, as well as the design of the combustion chamber. Understanding the distinctions between SI and CI combustion processes is fundamental to comprehending the design and operational differences between these two major categories of internal combustion engines. Factors such as ignition timing, fuel injection characteristics, and combustion chamber design significantly influence engine performance, emissions, and efficiency. Section 9. Knocking on trouble's door. Abnormal combustion. While the combustion process in internal combustion engines is carefully controlled for optimal performance, deviations from ideal conditions can lead to abnormal combustion phenomena, such as knocking or detonation, which can negatively impact engine performance and longevity. In SI engines, knocking occurs when the fuel-air mixture auto-ignites before the spark plug fires, creating multiple flame fronts that collide, producing a characteristic knocking or pinging sound. This uncontrolled combustion can lead to excessive cylinder pressures and temperatures, potentially damaging engine components. In CI engines, a similar phenomenon known as diesel knock can occur if the fuel ignites too quickly upon injection, resulting in a rapid pressure rise and a harsh knocking sound. Diesel knock can be caused by factors such as incorrect fuel injection timing, low cetane number fuel, or inadequate combustion chamber design. Abnormal combustion in both SI and CI engines can lead to reduced power output, increased fuel consumption, and elevated emissions. Factors contributing to abnormal combustion include low-quality fuel, high compression ratios, improper ignition timing, and excessive engine load. Preventing and mitigating abnormal combustion involves optimizing engine design and operating parameters, as well as using fuels with appropriate properties. Understanding the causes and consequences of abnormal combustion is crucial for ensuring the smooth, efficient, and reliable operation of internal combustion engines. By addressing factors contributing to these phenomena, engineers strive to maximize engine performance while minimizing potential damage and environmental impact.